So suppose p is a polynomial with degree d greater than 0. We're going to prove the last piece, which is part D, and this is very, very similar to the fundamental theorem of algebra. It's the most important theorem in all of algebra, leads to all different types of discoveries, and is incredibly, incredibly important. And this is very, very close to, very rigorous proof of this theorem. So you should be very proud of yourself for daring to come this far and for muddling through the confusion with me. So if you have not done so already, review part C. We're going to use that. I'll talk about that in a second, and watch that video. Here we go. So using part C, show that p of x can have at most d distinct roots. That is, there can be at most d numbers, all of them different, r1 through rd, with p of r1 being equal to, and all of these, p of r2, p of r3, so on and so forth, is equal to p of rd. All of these are equal to 0. Meaning, if I plug in any one of these values into my function, to my polynomial, I'm going to get 0. In other words, saying these are each a root. All right, so it's important to just remember that these are the roots. And it's also important to say that we're showing they can have at most d distinct. What does distinct mean? It means they're all different. So each of these numbers are different. So to recap, we are trying to prove that there is no way that if you have a polynomial of degree d, that you can have more than d distinct roots. And you think about this, this makes sense, right? When we've had polynomials of degree 3, we are expecting 3 roots. And this is going to be a proof that there are, at most, you cannot have more than 3 distinct roots. And we're going to use part C. So let's just carefully recap what part C said. So part C was very simple. It says if you are given a root, meaning if p of some number is equal to 0, then what's the case? Well, remember that if we have a root, we knew that the value of x minus that root goes in, or is evenly divisible into, p of x. In other words, then x minus r is a factor. The definition of factor, remember, means that it goes in evenly. A good example is 2 is a factor of 10 because it can be it evenly goes into 10. It goes in 5 times. I can write it 10 equals 2 times 5 plus 0. There's no remainder. So we're going to remember this. If we're given a root, then we know that x minus that root is a factor. And we're going to apply this over and over again in our proof. All right, so now we want to think about how we're going to prove this. So how would we prove that you can have d but no more than d distinct roots? And Omar did a great job today realizing the way that we're going to prove it. So we'll call it Omar's method. And the way that I like to think about this is, how would I prove that I can't jump more than 10 feet in the air? How would I prove that? Well, it's not good enough simply for me to jump 10 feet in the air. I can't, if I jump up and I touch something that's 10 feet above the ground, I've proven that I can touch something that's 10 feet, but I haven't proven that I, at most, can touch something that's 10 feet. To show that I can't touch anything more than 10 feet, I then have to set the bar just a bit higher, try and jump and touch that, and show that I cannot touch that. And so Omar's thought was this: if we want to show that you can't have any more, that at most you can have d numbers that are roots, let's pretend there was one more, d plus 1. And then we'll show that that is wrong, that that can't be the case. This is what's called proof by contradiction, or reductio ad absurdum, which means we assume that something is the case. So we're going to assume there's d plus 1, and we'll show that if there's d plus 1 roots, everything goes apart, that it ends up telling us something that can't be true. And if you assume something, and so if we assume that there's d plus 1 roots, and then we show that from that we get something that's impossible, well, then you know we must have assumed the wrong thing, and that can't be the case. So the first step is that we are going to assume there are d plus 1 roots. Assume p of x has d plus 1 roots. And we'll list them out. They are R1 all the way up through RD plus 1. All right. Now, let's pause for a second and let's think about how we could show that something ridiculous must happen. What can we do with each root? What are we given from each root? If you go back to part C, you'll notice that each root tells you a factor. So what if we factored, we came up with all of the factors? How many factors would we come up with? Well, you'd be correct in saying that we'd come up with d plus 1 factors. And that should raise a red flag, because if the degree of your polynomial is d, well then how could you have d plus 1 factors? Because each factor will increase the degree of your polynomial by 1. So if you had d plus 1 factors, your degree would have to be, you guessed it, d plus 1. So our goal is going to be to use C to find all of the factors. We'll go all the way through each one, and we'll show that if we try and have d plus 1 of them, everything falls apart. That we're okay up until d, but once we hit d plus 1, as Omar predicted, we are going to end up with something that is quote-unquote wrong, just plain wrong. So let's start at the beginning. From part C, we know what? Well, let's start with R1. So from part C, we know, well, what do we know? If we look at R1, we know that x minus R1 should be a factor. So we know that P of x is equal to x minus R1 times some other polynomial. Now, what is that polynomial going to be? It's going to be some polynomial. What's the degree of it going to be? I know that, we might want to keep track of this. I know that P of x has a degree of d. I know that this has a degree of 1. So what will the degree of my polynomial be? It has to be, we're going to call it P1 of x. The degree of it has to be d minus 1. And it's going to be important to keep track of the degree, and here's why. If I have a degree 1 polynomial, when I multiply it by another polynomial, the degree, this degree 1 will make the degree of this polynomial increase by 1, right? X to the 4th times just a single x will make it x to the 5th. So if you imagine if this were a 5th degree polynomial, you'd have a 1st degree, and this other one would have to be a 4th degree, right? We've seen this all the time. If you have a d degree polynomial, you should have d factors. So if you have one factor taken out, you'll have d minus 1 left. Okay? The other way to think about it is that if you were to take this polynomial of degree d and divide it by x minus r1, this polynomial of degree 1, you'd be left with a polynomial of degree d minus 1. So this is the polynomial we'll get if we divided p of x by x minus r1, and notice that when we do that division, it would go in evenly from part C. That's what we proved. So this polynomial will have no remainder going on, right? And that makes sense. Okay, now this next move is the tricky move. Okay, this is the kind of ingenious idea. And what we'd like to show is we'd like to come up with all the other factors, right? And the question is, how are we going to do that? Where are the other factors lying? Where is x minus r2? Well, x minus r2 isn't here, right? Can't be there. So x minus r2 must be some part of p1 of x. Remember, p1 of x has a degree d minus 1. So from our knowledge of polynomials, we know that this must be made up of some number of factors. We're thinking d minus 1 factors, right? So when we plug in r2, right, we know that we're looking for something to do with this polynomial. So the tricky move that we make is we plug in r2, okay? So p of r2. Well, what is that equivalent to? Well, let's remind ourselves, right, that p of r2 is a root. So when I plug in r2, what should I get? I should get 0. Okay, well, when I plug in r2, I'm going to have r2 minus r1 times p1 of r1. I'm sorry, of r2. Now, these two things multiplied by each other must equal 0. Can this be equal to 0? You might want to say yes, but think about it. Go back to what we are working with. If something minus something is 0, those two somethings must be equal, right? 5 minus what is 0? 5 minus 5. So these numbers would have to be the same, but we said that d distinct roots, right? These are all distinct. In other words, different. So this can't be 0, which means what? It means that this has to equal 0. So, since r2 minus r1 is not equal to 0, p1 of r2 must be equal to 0. What does that mean? Stop for a second and look at this. What does that mean that r2 is for our polynomial p1? If I plug in r2 to p1 of x, it's got to equal 0, meaning that r2 is a root of p1. And that's perfect because we wanted to come up with the factor x minus r2, and we said that we think it will be in p1, meaning that r2 would have to be a root of p1. And lo and behold, there it is. So that's the big move, is noticing that r2 has to be a root of p1 of x, because that factor has to come out of p1 of x. And so we plug in r2, and lo and behold, p1 of r2 has to equal 0. So by part C, I'll just say by C, we have what? Well, what do we know? We know that if r2 is a root of p1, that means that p1 of x, that what is a factor of p1 of x? X minus r2. So we take x minus r2, and we'll multiply, right? X minus r2 is a factor, and that means it goes in evenly, so we must be able to get back p1 of x by multiplying x minus r2 by some other polynomial. We'll call it p2 of x. Okay? Now it's important to note the degree of these polynomials. Okay? What is the degree of p2? The degree of p2, think about it, the degree of p1 is d minus 1. We have our factor, which has degree 1. So the degree of p2, well, when I multiply it by a degree of 1, it's going to increase by 1, and then I want it to end up being d minus 1. Also think about if I took a degree d minus 1 polynomial and divided it by a degree 1 polynomial, do the division, just think about it, you're going to end up with something 1 less than this.